Good morning, students. Today we are going to study about the impulse response. The general form of any difference equation having an order capital N can be given by 1 plus summation coefficient a suffix k y of n minus k, range of k from 1 to capital N, equal to, I'm writing it in the next line, summation of coefficient b suffix k x of n minus k. Range of k is from 0 to say m, where n is greater than m. Impulse response means the input to the system is a delta function. Therefore, for an input xn equal to delta n, the above equation can be written as 1 plus summation of ak y of n minus k, k from 1 to capital N, equal to summation of bk. Instead of x n minus k, I am now writing it as delta n minus k, k equal to 0 to capital N. If the value of n is greater than m, then this equation will be reducing to a homogeneous equation. Homogeneous equation form is a suffix k y of n minus k equal to 0. K will be from 1 to capital N, and the value of coefficient a0 will be equal to 1. We can obtain the homogeneous solution of this particular equation and impose the initial conditions to determine the arbitrary constants of a0, ak, and so on. If the value of n is equal to m, then we have to add an impulse function to the homogeneous solution. So based on this now, we will solve a problem. Suppose the question is, we have to find out the impulse response for the system which is described by a second order difference equation. The second order difference equation is y of n 0.6 y of n minus 1 minus 0.08 y of n minus 2 plus xn. Question is, we have to find out what is the impulse response hn. So how we will proceed for this particular sum? So I'm starting the solution over here. The total response, if I denote it by yn, it is the summation of a homogeneous solution and a particular solution. These are the two parts. So that means we have to calculate what is the value of this and this. Now for an impulse response, we know xn is equal to delta n. So in that case, the particular solution will be equal to 0. So from the previous equation, if I name this equation as equation 1, so from equation 1, I can say the solution yn is equal to yHn. That is the homogeneous solution. Now, how do we find the homogeneous solution? To find this homogeneous solution, we have to do one substitution. So, what is that substitution? Substitute we have to do is xn equal to 0. We have to do this substitution. So, when we do this, then the equation will become y of n minus, equation means I'm talking about the original equation, okay, 0.6 yn minus 1 plus 0.08 yn minus 2 equal to 0. Let this be equation number 2. Let the solution be for equation number 2 be yHn equal to lambda raised to the power n. So now we have to find out what are the roots of the characteristic equation. So when we substitute this in equation number 2, we get lambda n minus 0.06 lambda raised to the power n minus 1 plus 0.08 lambda raised to the power n minus 2 equal to 0. So when we want to solve the roots of the characteristic equation, we have to get the roots of the characteristic equation. So we will take over here common lambda raised to the power n minus 2. So this becomes lambda square minus 0.06, sorry, 0.6, it is not 0.06, it is 0.6. So this will be 0.6 into lambda plus 0.08 equal to 0. So the characteristic equation is lambda square minus 0.6 lambda plus 0.08 equal to 0. So we have to find out what are the roots of lambda. When you solve this equation, the roots of lambda will be coming around 0.4 and 0.2. So the solution of the homogeneous equation will be yHn equal to C1 lambda 1 raised to the power n plus C2 lambda 2 raised to the power n. So C1 we have to find out, lambda 1 is 0.4 raised to the power n plus C2 0.2 raised to the power n. So let this be equation number 3. Now from this equation number 3, if the value of n is equal to 0, then we can say y of 0 will be simply equal to C1 plus C2. So this is equation number 4. And if the value of n is equal to 1, then we can write y1 is equal to 0.4 C1 plus 0.2 C2. This is equation number 5. Now if we go back to the original difference equation which is given in the problem, then on substitution y of 0 will be equal to 0.6 y of minus 1 minus 0.08 y of minus 2 plus x of 0. Now this x of 0 is your delta function, so this value will be equal to 1. And this values y of minus 1, y of minus 2, these are all equal to 0. So therefore we can write y of 0 is nothing but 1. Similarly, if we go back to the original difference equation, we can have y of 1 as 0.6 y of 0 minus 0.08 y of minus 1 plus x of 0. So here we can have, sorry, not x of 0, this will be x of 1. Now what is x of 1? Because this is a delta function, therefore x of 1 will be equal to 0 over here. This y of 0 we have calculated, this is equal to 1, and this y of minus 1 is equal to 0. So from here y of 1 will be simply equal to 0.6. So now we can write, if we substitute these values of y0 and y1 in the equation numbers 4 and 5, then we can have C1 plus C2 equal to 1 and 0.4 C1 plus 0.2 C2 equal to 0.6. So we get two simultaneous equations, equation 7 and equation 8. When we solve these two equations, we will get the values of C1 and C2. C1 will come about 2 and C2 will come about minus 1. So these values, when we substitute over the original equation over here, I'm talking about this equation number 3. Okay, then we can have the solution as equation number 3 is this one. That is C1 into 0.4 to the power n. So yn is equal to 2.4 to the power n un minus C2. C2 value is minus 1. So minus 1 into 0.2 raised to the power n un. So this is your resultant response. Next we move on to step response. Step response can be expressed with the help of impulse response using convolution sum. How it is done? Let us say we have a discrete system with impulse response Hn and step response Sn. Okay. Then Sn can be represented as the convolution of Hn and Un. So this can be again rewritten as summation of hk u of n minus k ranging from minus infinity to plus infinity. Since u of n minus k is equal to 0 for all values of k greater than n and u n minus k is equal to 1 for all k less than equal to n, we can write Sn equal to summation of hk k from minus infinity to n. Okay, so that's all for step and impulse responses. Next, we move on to frequency analysis of discrete time signals. You can expect a short note on this in your exams. Any continuous time signal, or rather a continuous time periodic signal xt having a time period capital T can be represented as the weighted sum of harmonically related sinusoids or complex exponential. If the signal is represented in terms of harmonically related sine and cosine function, then the series which will be obtained is called a trigonometric series. So this we have already studied in circuit theory and mathematics classes. So xt can be represented as summation of a0 plus an cos of n omega naught t plus bn sine of n omega naught t, n ranging from 1 to infinity. All these constants a0, a1, a2, a3 up to an, then b0, b1, b2, b3 up to bn, these are known as Fourier coefficient. This omega naught is known as fundamental frequency. So omega naught is equal to 2 pi by t. Similarly, in terms of exponential Fourier series, we can write it as xt equal to cn e to the power jn omega naught t from minus infinity to plus infinity. Here, the cn coefficients will be known as exponential Fourier series coefficient. These Fourier series coefficient Cn are complex value. So we can write it as Cn and similarly we can have C of minus n as mod of this negative sign. The power of a periodic signal xt is given as This particular equation is known as Parseval's relation for power signal, and the plot of the magnitude of Cn square as a function of the frequencies NF is known as power density spectrum or line spectrum. Now this is for your continuous time periodic signal. What happens when we move for discrete time exponential signals? Let us see that. Unlike the continuous time domain signals, all discrete time exponential signals may not be periodic. So a discrete time periodic signal or a discrete time exponential signal e to the power j omega naught n is periodic only if omega naught is a multiple of pi. The fundamental frequency of such signals is given by omega naught, which is equal to 2 pi by capital N, and N is your fundamental period. So the periodic sequence can be represented as a linear combination of the exponential e to the power j 2 pi kn by capital N. So the expression of this will be xn. Instead of cn, we will write as ck e to the power j 2 pi by capital N multiplied with kn. Okay, this is the expression for exponential Fourier series in case of your discrete time signal. The value of ck is 1 by n x of n e to the power minus j into 2 pi nk by capital N. So this range of k you can write from 0 to capital N minus 1. So the values of k will be from 0, 1 to n minus 1 over here. And similarly, the value of n for this equation can be written from 0 to n minus. So that's all for today's class. Thank you.